All right, so now we're going to talk about first order linear differential equations. So far we've only been able to solve explicitly separable differential equations, and that was kind of limiting. There were a lot of differential equations that we still couldn't solve. So now we're going to introduce an extra type that we can solve. What does this mean? First order means we only have y prime and y. We can have y in the equation, y prime in the equation. No higher order derivatives, no y double prime, y triple prime, etc. Linear means it needs to be linear in these variables. So we can't have y squared, we can't have crazy functions like sine of y prime. Linear in the y's. Does not have to be linear in the t's or x's. In the independent variables. Does not have to be linear in independent variables. So a perfectly valid equation would be y prime plus t squared y equals sine of t. This is not linear, but that's okay. Those are the independent variables. It is linear. I don't have any funny business going on with the y and the y primes. And then differential equations are equations with y and y prime in them. That's what we've been working on, what we will be working on this whole class. Okay, so first let's look at an equation that we've solved already. dy by dt minus 3y equals 0. And this we said was separable. So we could solve it by separating the variables. Remember let's do some of it quickly. dy by dt is 3y. We needed to keep the d stuff on top. So we're going to multiply both sides by dt and then get the y with the dy, divide both sides by y. So that was 3 dt. And then we had like this domain thing, y couldn't be 0, but we fixed it later. And then we integrated both sides and we could solve that. We ended up with y equals k e to the 3t, where k was any real number after we fixed the domain stuff. Okay, now let's look at a different way to solve it. I have a dy by dt and a y. What other thing from calculus has that in two different terms? A product rule kind of does. Can I make this look like a product rule? Why would I want to do this? I wouldn't in this case. I have a perfectly good solution for this differential equation, but this will allow me to solve other differential equations where maybe this side isn't 0 and it's not separable. Okay, so can I make a product rule? Not really, because -3, I want -3 to be the derivative of something, which maybe it's the derivative of -3t, but I don't have that over here, so that's not very good. But I can exploit a very important function, which is e to the something. That thing, when you take the derivative, it sticks around, and we can introduce other constants. So like, what if I multiply both sides by e to the something? That's really the whole theme of this lecture. Multiply both sides by e to the something. E to the what? E to the thing whose derivative is -3. So e to the integral, basically, of -3 dt is what I'm going to multiply by. Well, this isn't a very hard integral. This is just e to the -3t. Check that out. I'm going to multiply both sides by e to the -3t. E to the -3t dy by dt is -3 e to the -3 times e to the -3ty equals 0 times that is just still 0. Now this is a product rule. The derivative of y is dy by dt. The derivative of e to the -3t is exactly this. So this is the derivative of e to the -3t times y. Take a minute to check that if you don't believe me yet. And then I can integrate both sides. So e to the -3ty equals integral of 0 is a constant. And then, so y is going to be c divided by e to the -3t, which is the same as c times e to the 3t. And then this constant was any real number. So those two solutions are the same. C is now k. Okay, as I said, wouldn't want to solve this way, but here's an equation that you would want to solve this way. let's look at this equation. dy by dt minus 3y equals 7 e to the 3t. And I'll actually make this an initial value problem so we can finish solving it. Y of 0 equals 9. Okay, this note is not separable. But we can do the same thing we did before, which is multiply by e to the something to make this look like a product rule. What are we going to multiply by? We're going to multiply e to the thing whose derivative is negative 3, so the integral of negative 3 dt. And I can take any integral, so I don't need a plus a constant here. Okay, well that's the same thing as before. That's e to the negative 3t. Multiply both sides by e to the negative 3t. E to the negative 3t dy by dt. This is looking the same as before. E to the negative 3ty equals 7. E to the positive 3t times e to the negative 3t is just 7. Those two things multiply to 1. Okay. This looks kind of like before. This is the derivative of, this is still that same product rule, right? The derivative of e to the negative 3ty equals 7. Now if I integrate both sides with respect to t, I get e to the negative 3ty equals, this is now 7t plus a constant. Getting y by itself, multiply by e to the positive 3t. We'll get rid of this. So y is 7t e to the 3t plus c e to the 3t. And I can sub in my 0, 9 to actually solve for c. So 9 equals, this part is 0, plus c times e to the 0 is 1, so c must be 9. So my solution to the initial value problem is y equals 7t e to the 3t plus 9e to the 3t. So what am I doing in general? What does this look like in general? I have a y prime plus, I can have any function of t here actually. Here I had a constant, but any function of t, we'll call it q of t, equals any other function of t over here. That's a first order linear differential equation in general. And then what I'm going to do is I'm going to make this look like a product rule by multiplying both sides by this thing, which I call the integrating factor. Factor because it's multiplied, integrating because it helps me integrate. Integrating factor is going to be e to the power of the thing whose derivative is this. So e to the integral of q of t dt. Let's look at another example. Let's look at an example where maybe it doesn't start in this format. This one started in this format. I had y prime by itself. What if I had t y prime plus 2y equals 4t squared? I'm going to write a few, I'll make it an initial value problem. Y of 1 equals a. And I'm also going to write t is greater than 0 as a domain restriction. We'll see in a minute why that's true. And a few lectures from now, we'll talk about existence and uniqueness, and that'll be important. Okay, so first of all, not in this format. I don't have y prime by itself. So I'm going to have to get it in this format. I will divide both sides by t. So y prime plus 2 over t y equals 4t. Okay, I already see that t can't be 0. So maybe this already helps. We'll talk more about specifically why that later. Okay, now I'm in this format. Now I can find my integrating factor. You can just always use the formula for this. E to the power of the integral of whatever's in front of y. So 2 over t dt. What's the integral of that? It's 2 natural log of absolute value of t. I don't need a plus c. I just need one thing whose derivative is 2 over t. So this should be good enough. This is, well, e to the natural log of something is the thing itself. So this is absolute value of t squared. And then absolute value is already non-negative. Square is non-negative, always. So I don't need the absolute value. T squared is the same as absolute value of t squared. Okay, great. Now that I have the integrating factor, I multiply both sides by it. Multiply both sides of this by t squared. So I get t squared y prime plus 2 over t times t squared is 2t y. 4t times t squared is 4t cubed. And I should have a product rule on the left this should be t squared y. Check that out. Derivative of t squared y is indeed this. And then I have whatever I have on the right. Integrate both sides with respect to t. T squared y equals integral of this is t to the fourth plus a constant. Divide both sides by t squared to get y by itself. Y equals t squared plus c over t squared. And then we can actually solve the initial value problem. Sub in, this is an a. A is a constant. So I'm going to sub in 1, comma a. A for y, 1 for t, 1 plus c over 1 is just c. So I get c is a minus 1. So my solution to this initial value problem is y equals t squared plus a minus 1 over t squared.